2.6 Common Forces. Here is an apple on the table. What is the net force on this apple? The total force. The apple is not moving, so it's 0. And both Newton's first law and second law will tell us that the apple will not move because there's no net force. So the net force is 0. Let's draw a free body diagram. Here's the apple. Are there any forces? Well, we know there's weight, the force of gravity. Some people write it as W, some people write it as F, G for gravity. Yeah. Okay. Is that it? Well, if that's it, the net force can't be 0 because we have weight coming down. In order for the net force to be 0, there must be another force pointing up. That force is called the normal force. There has to be, otherwise the apple will move down. So the question is, what is keeping the apple up? Okay, what is keeping the apple up? Well, what is keeping the apple up? The table is. So the normal force is the table pushing up on the apple. So the normal force here is the table exerting a force on the apple upwards. Okay. So if we have a box and a table, there are two forces on this box. Weight is the box. The weight is 80 newtons, and the weight is actually the force of gravity pulling down on the box. We'll learn about what that means later. Really, what's happening is the Earth is pulling the box down. The normal force is also 80 newtons. Is the table pushing up on the box. So the table pushes the box up, the Earth or gravity pulls the box down, and the net force is 0. Here, again, we have two forces, weight, and I'm going to write Fn for normal force. The normal force. What is the normal force? Well, what is pushing the cup or the juice up? The table exerts a force on the cup, and we know it's upwards. That's the normal force. Here we have a child sitting on the chair. What's the weight? Well, F equals ma. M is 25. We're on Earth, so A is about 10. So F is 25 times 10. 25 times 10 is 250 newtons. And we know that's downwards. So the weight is 250 newtons downwards. The net force is 0. So we know right now we have the weight is 250 newtons down, which means there has to be the same amount of force going up. That's the normal force. So the normal force, well, the chair is exerting a force of 250 newtons upwards on the child. The chair is keeping the child up. Okay. What happens if objects are moving? We're pushing it into the left or to the right. So actually it doesn't matter whether the object is moving. What matters is whether there are forces to the right or to the left. So the person is pushing the cart with a force of 20 newtons. So let's do it over here. So we know that this force is 20 newtons. It's going to the right. The friction force is 3 newtons. The friction force is always opposite of the direction of motion. So that's to the left. So we have 3 newtons of force going to the left. The mass is 1.5 kilograms. Identify all the forces and draw a force diagram on the cart. Here's the cart. So we know that there's a force of 20 newtons going this way. And that's the pushing force. We have to identify the forces, give the name, so the pushing force is going this way. Friction is 3 newtons, so it's a lot smaller. So that's friction. Friction. Next, we know there's weight. How much is the weight? Well, weight is F equals ma, which is 1.5 kilograms times about 10 meters per second squared. So it's about 15 newtons. So we know that the weight is 15 newtons, and that's our weight, or the force of gravity. That means that the normal force also has to be 15 newtons. That's the normal force. Okay, that's the normal force. Because the cart is not going up, it is not going down. So the normal force and the weight must be equal. The net force, well, the 15 minus 15 is 0. They cancel. So net force is really 20 minus 3, which is 17 newtons to the right. So we have 20 minus 3 is 17 newtons to the right. There's a net force. From Newton's second law, we know if there's a net force, there's an acceleration. If there's F, there's M. There's A. So the cart will accelerate. Okay. For this one, once we know the net force, we can find the acceleration. So the mass of the cart is 5 kilograms, so the weight is 5 times 10, which is 50 newtons. So the weight is 50 newtons. So we know the weight is 50 newtons. That means that the normal force is 50 newtons, because they have to cancel each other out. We have a pushing force going to the left of 40 newtons. And we have a friction force going 10 newtons to the right. And that's friction. So the net force, well, the 50 minus 50 cancel each other out, so it's 40 minus 10, which is 30 newtons to the left, because the pushing force is larger and it's going to the left. Once we notice, we can find the acceleration. F equals ma. M is 5. The net force is 30 newtons to the left. So 30 newtons is equal to 5 times A. We divide both sides by 5. And when we do that, we're going to get 6 equals A. So 6 equals A. So the acceleration is 6 meters per second squared to the left, because the force is to the left, net force. Finally, what if we have the same problem, but it is now frictionless? Frictionless means no friction. So I can erase the friction. That means that this time the net force is just 40 newtons. So force is 40. Mass is still 5. 40 equals 5A. Divide both sides by 5. And we'll get the acceleration is 8. So the acceleration is 8 meters per second squared to the left. So when there's no friction, frictionless, this one accelerates more. Okay, that's it.